Right. So what we were doing last class was to look a little more. Just to recap, like expectations of random variables and expectations of functions of random variables. Okay. So in particular, we were looking at things like this z1. So let's say x1 and x2 are two random variables defined on the same space. Okay, and we ask questions like, what is the expectation of x1 and x2? Okay, so in particular, we were interested in this form, and the way we would write this is to say summation over all elements in the universe, the probability of omega, x1 of omega times x2 of omega. Okay, but we can also simplify this as you sum over all the values x1 can take and sum over all the values x2 can take. Okay, and you write the joint probability that x1 can take value little x1 and x2 can take value little x2. Okay, now this is the event that is the intersection of the event that x1 takes on value little x1 and x2 takes on value little x2. Okay, times little x1 times little x2. Okay, and we said last class that if x1 and x2 this weight was due today before class.
Yes, that's what I thought too. Quiz 8 was due today.
Oh, maybe I'm wrong. Oh yeah, that is true. So you're right. You're right. Quiz 8 was due today. I'm sorry. Like
Yeah.
sometimes I get confused between the two classes. For the other class, quiz 8 is due Friday. So that's where I got confused. Okay. Okay. So you want me to go over which question in quiz 8?
Question 3.
Question 3, which is okay.
29 midterms.
Okay. So right. Oh, so for the few of you who got like an auto submit on quiz 7, I think there may be 3 of you in class. I'll figure out. I'll have to make a new makeup for you. Okay. So just hold on, and I'll get in touch with you. Okay. So okay. So quiz 8 is like, what's the probability that the probability of the set AI, right? So we'll go over that. Okay, so let's do one thing. Let's try to finish up what we started, rather than like going from one topic to another, jumping too much. Okay, and I'll try to I'll try to include that question within today's lecture too. Okay, so I haven't forgotten about it. I'll get to it. Okay.
Oh, quick question on the lecture. The first line, is that assuming that the two variables are independent or not?
No. They're defined on the same space means like that. Remember that these two are functions. This is a function from a universe to real numbers. This just means that this is another function from the universe to real numbers. That the universe is the same for both. Right? So remember that each random variable is just a function from a universe to real numbers. Okay. When they say there are two variables defined on the same space, they're defined on the same sample space. Okay, or maybe this will make it more clear. Right, so they're just two functions defined on the same sample space or the same universe. They exist in the same universe. Okay, does that make sense?
Yes.
Okay. Also, if you can turn on your videos, right? So, okay. So last class we also saw that if x1 and x2 are independent, then expectation of x1, x2 is the product of their expectations. Okay, but the converse is not true. Okay. Okay, the converse is not true in general. Okay, so we had this example where we said x1 and x2 can take values like this. I may be getting the sign wrong, but that's not a, it's not like a big issue. So I think 1/6 is 6. Right? And we computed last class that here the expectation of x1 is equal to 0 and the expectation of x1, x2, right? And to compute the expectation of, let's do this again. How do we compute the expectation of x1, x2? Right, so this is, so we write x1, x2 here. So here it is plus 2, here it is minus 1, here it is minus 1, and here it is plus 2. Right, so the expectation of x1, x2 is 2 times 1 over 6 plus minus 1 times 2 over 6 plus minus 1 times 2 over 6 plus 2 times 1 over 6, which is 0. Okay, and same way the expectation of x1, you can compute this one, you can do it like this as well, minus 1 times 6 plus minus 1 times 2 over 6 plus 1 times 2 over 6 plus 1 times 1 over 6, which is 0. Okay, right? So here, expectation of x1, x2, which is 0, equals the expectation of x1 times the expectation of x2, which also happens to be 0. Okay, we don't need to compute the expectation of x2 here because really doesn't matter, because product of the expectations of x1 and the expectation of x2 is 0 because expectation of x1 is 0. Okay, does that make sense? Okay, and so we said last class also that x1 and x2 are not independent, but we were kind of hurried about it. So let's just do it again properly. I mean, x1 and x2 are not independent. We can do this the brute force way. Okay, so what is the distribution of x2? Right, so x2 is a random variable that takes values. So what are the values x2 takes? All the different values that the random variable x2 can take. Okay, yeah. I'm just sorting out in ascending order. Okay, what are the probabilities of these values? Right, so just a second. Okay, can you speak up a little bit, please? Like I can't hear. Okay, so what's the probability x2 is negative 2?
Yeah, that one's 1/6.
1/6, very good, because this is the only case where x2 is negative 2. Okay. What is the probability x2 is negative 1?
2/6.
And this is also the probability x2 equals 1. probability x2 equals positive 2 is again 1/6. So everyone okay with this? Okay, we are simply getting this from the table. Okay, but what's the probability x2 is negative 2 given x1 equals negative 1? Right, so this is the joint probability x2 is negative 2 and x1 equals negative 1 divided by the probability x1 equals negative 1. Okay, and the joint probability x2 is negative 2 and x1 is negative 1 is this line. Okay, and this is 1/6. Okay, and the probability x1 is negative 1 is these two lines, and together the probability is 1/2. Right, so this is 1/3. Okay, and so clearly it is not equal to 1/6, right, and therefore they are not independent. Okay, but you could see it very simply by looking at a different conditional probability. What is x2 equals negative 2 given x1 equals 1? So Caleb, you're muted.
Be the joint probability of x2 equals negative 2 and x1 equals 1.
Right, right, but what's the probability x2 is negative 2 and x1 equals 1?
It's 0.
0. Right, so this event has probability 0. So x1 equals 1 has probability 1/2. Right, so this probability is 0. Okay, it's like saying when x1 equals 1, it takes on a different set of values from when x1 equals negative 1. Right, so the value of x1 even determines not just the probabilities, it even determines which values x2 can take. They're definitely not independent. Okay, so right, so that's why like I could see this, that's why I told you they are independent, sorry, they're not independent even without doing any calculation. Okay? You don't actually have to do calculations, you just have to see that this set of values is actually different from this set of values. Okay, so the value of x1 even determines what values x2 will take, like clearly not independent. Okay, okay, so good, so are we good on this?
Could you say that last part again?
Right, so here like I'm saying that we don't even have to actually compute any probabilities to see that x1 and x2 are not independent. The reason is that the values x2 can take, okay, when x1 is negative 1, it's a different set of values that x2 can take when x1 equals 1. Right, so this means, for example, when x2 equals negative 2, what is x1?
What did you ask again?
Right, so what's the probability x1 equals 1 given x2 is negative 2?
Oh, 0.
No. Oh, sorry. Yeah, this is probably 0. Sorry. Yeah, this is 0. What's the probability x1 equals negative 1 given x2 equals negative 2?
Oh, that should be 1. Right?
1. Right? So here, like when x2 is negative 2, you know for sure that x1 has to be negative 1. Okay? And same thing, when x2 is 1, you know for sure that x1 has to be negative 1. Okay? So clearly, they're not independent. Okay, you completely know what x1 is by just looking at the value of x2. Okay, so is everyone okay with this? Okay, so good. So, but the moral of the story, the bigger moral of the story, is that even though the expected value of x1 and x2 equals the expectation of x1 times the expectation of x2, okay, they're not independent. Okay, we have a different, but we still like this equality. Okay, it still tells us something. It does not tell us that they are independent. Okay, but we give a different name for random variables that satisfy this. Okay, we call, okay, we say we need a different word because we know that simply if the expectation of the product equals the product of the expectations, we know that they're not necessarily independent, so they're not that strongly separated. Okay, so but this is still something, right? This is still something interesting. Okay, so we need a different name for that and we call them uncorrelated. Okay, so if x1 x2 is equal to expectation of x1 times the expectation of x2, we call x1 and x2 to be uncorrelated, and then we look at the previous sentence that said if x1 and x2 are independent, so we are recalling this. Right? So if x1 and x2 are independent, it's actually stronger statement, okay, because we automatically get that they are also uncorrelated. Okay, so uncorrelated random variables are not necessarily independent, okay, but independent random variables are uncorrelated. You can think of it like this, like if this is just like a caricature. Okay, so if I take all combinations of random variables that are independent within this small circle, okay, then uncorrelated random variables are a larger circle. So these are all the uncorrelated random variables. Okay, so everything that is independent is also uncorrelated. Okay, but everything that is uncorrelated need not be independent. Okay, right. We are good on this. Okay, so we were looking at this and we also defined the variance. Okay, we defined the variance because for a random variable, we said that there's a limitation to how much an expectation can tell us about the random variable. It tells us something, but not everything. Okay, so it's one number after all, and the random variable is a function. Okay, so we cannot hope to capture the entire function with one number. Okay, but it's still something, it's a start. Okay, and we decided we are going to think of the expectation as like a first order approximation to the random variable. The second order approximation to the random variable is the variance, how the random variable is distributed around the expectation. Okay, so in particular we said let z be any random variable. Okay, z is the variance of z is also an expectation, but it is the expectation of z minus the expectation of z whole square. Okay, now keep in mind with this is just a number. The expectation of z is just a number, it's a single number. Okay, so just so we don't get confused, okay, just so we don't get confused, we'll think of this as expectation of z minus a squared. Okay, and we'll substitute back for a later on. Okay, but first let's simplify this. Okay, this is the expectation of z minus a squared. This is a number which Okay, so but we don't want to get confused just because we see this boldface C. Okay, right. So tell me, how would I simplify expectation of z minus x squared? Right, so this is same story, like summation of all points in the universe. Can somebody complete? Okay, Brandon, can you help me? Right? No, so how do we write the expectation of any random variable? Okay, it really doesn't matter what is there here, right? We always start in the same way. Okay, right, value times the probability. Okay, so the probability of this outcome in the universe times the value of the random variable on this outcome, and this is just z of omega minus a square. Okay, is everyone okay with this? Okay, always the same story. There aren't too many stories here, so it's always the same thing. It's how far you can go with this, right? Now this part is now a number. Okay, just simplify it. So this is z squared w minus 2 times a times z of w plus a squared. Okay, but you know expectations are linear, or rather, like, we don't need to know, but we can rearrange this sum. I'm going to use the same dummy variable in each of the summations, not the greatest formal way to do it, but it's okay. Okay, so what is the first quantity? This next, James, what is this quantity?
I'm not sure.
But what does it look like? It's probability times a value and the summation of all of this, so it is some expectation. Okay, what is it the expectation of? No, but you see what we did here, right? You see what we did here, right? Expectation of z minus this one. We wrote probability of w times the evaluation at that point. Okay, so the same pattern.
Sorry, no, I had to respond to a text message and I totally missed everything for a second there.
Oh, okay. So here, like, we are writing the way we do this, right? So when we have expectation of, sorry, okay, when we have expectation of x1, x2, okay, what we do is like probability of every outcome times x1 of omega, x2 of omega, summation over all outcomes. So that's what it is. Okay, evaluation of whatever you have here, you evaluate it here. Okay, right? And you take the weighted average over all probabilities in the weighted average, weighting it with the probability of outcomes and sum over all outcomes. Okay, so that's the expectation of x1, x2. Now the expectation of z minus a squared, okay, was just the weighted value of z minus a squared, right? So you see this and you see this. Okay, now the same way, what is this quantity? It's the weighted value of z squared.
ZW times ZW?
Right, no, but what is it the expectation of, right? So we wrote expectation of z minus a squared is the weighted value of weighted average of z of omega minus a whole square. Okay, so what is this the weight? So this is the weighted average of z squared. So what is it? So this is just the expectation of z squared. Okay, so okay, the way we would compute the expectation of z squared was literally this. Okay, now tell me what is this quantity?
Expectation of a plus z squared.
Whatever you have here, you have to just say whatever you have here.
A z omega.
2 times 8 times z.
Oh,
Okay, right? So, but we are going to simplify this, but I'm just saying this. What is this the expectation of?
a squared.
Right, expectation. Okay, so is that clear? Right, okay, so now look at this summation. In this summation, 2 and a are just numbers. They do not depend on omega. Okay, so you can use the distributive law to just move 2 times a outside. Okay, because in this summation, this is a summation over omega. 2 and a are just numbers. Okay, so you can just move them out of the summation. In this square, in this problem, in this summation, right, a squared is just a number. I can just move it out. Okay, everyone okay with this? Okay, now James, can you tell me what is this summation? So there is 2a, and what is this summation?
Ez.
Right, so the expectation of z.
Right.
Okay, and what is this?
Expectation of probability or no?
No. Whatever is there here, here it's a 1. Okay,
One.
right, but there is more to it. What is the sum of all the probabilities? Okay, so here I'll write expectation of 1, but we can actually do better than that. Okay, here, what's the sum of all probabilities? The sum of all these probabilities is 1. So this term is actually just literally plus a squared. That's all it is. Okay, sorry, this one was minus 2a. I apologize, my typo. Right, so this was a minus, so should have kept a minus. Okay. Okay, so is everyone okay with this? Okay, so in particular, like this is how we write expectations. We are also using it to get some practice on this. Okay, now remember that here for the variance of z, so this is the expectation of z minus a squared for any number. Okay, but the variance of z is the expectation of z minus the number we use is just expectation of z. Okay, and so this is expectation of z squared minus 2 times the expectation of z times the expectation of z plus the expectation of z whole square. Okay, all I've done here is instead of a, I've written this number. Right? So do you see what I've done? Every time I see an A, I've written this number expectation of Z. Okay, that's literally all I've done. Okay, but lucky for us, there is a simplification going on here. Okay, this is just minus 2 times expectation of Z squared. Okay, and this is plus expectation of Z squared. Okay, and so together like minus 2a squared plus a squared. Okay, and that is minus okay. Now the right, so is everyone okay with this? Right, so this is the variance of z. It is related to expectation of z squared. Okay, it's a little different from expectation of z squared because we subtract out square of the expectation. Okay, now keep in mind these are two very different quantities. Okay, keep in mind that expectation of z squared is summation probability of all outcomes in the universe z squared of omega. Okay, and expected by expectation of z whole squared, what we mean is summation very different quantities. They're not the same. Okay, by convention, like I mentioned this before, but I'll repeat it again. Whatever is there immediately to the right of this operator e, okay, that's what it's the expectation of. Okay, so the z squared sticks to the expectation. Okay, if we want to write this quantity, I write expectation of z. I need parenthesis here because in this case only z sticks to the expectation, and I square that number. Okay, and these are two different numbers. Okay, and in fact, like you can show that this is always greater than or equal to 0. Okay, this quantity expectation of z squared will always be greater than or equal to 0. Or will always be greater than or equal to the expectation of z whole squared. Okay, it's not very difficult to see because you know that this quantity has to be positive, because no matter what a is, this quantity is a square number. It's a weighted average of just square positive numbers. Can never be negative. Okay. Okay, so the variance of z we know is definitely positive. Okay, or rather variance of z is definitely non-negative. Okay, it really doesn't matter what you do, you can never get variance to be a negative number. Okay, because the variance is the weighted average of z of this quantity, z of omega minus some numbers whole squared. Really doesn't matter what z of omega is and what this number expectation of z is, the square of that is always non-negative. Right? Does everyone see that? Right? And because it's a weighted average of only non-negative numbers, okay, variance of z has to be greater than or equal to 0. But because variance of z has to be greater than or equal to 0, and variance of z equals, okay, and variance of z is expectation of z squared minus open parenthesis expectation of z whole squared. Okay, it follows that this quantity, this difference must always be greater than or equal to 0. Or in other words, we know that the expectation of z squared is always greater than square of the expectation of z. Okay, the two different quantities, do not get confused with expectation of z squared and square of the expectation of z. Okay, so we are good on this. Okay, so in fact, this computation, we did it so elaborately for a different reason. It also gives us a different interpretation for the expectation of z. Okay, now look at this quantity, expectation of z minus a squared. Okay, so this quantity, expectation of z minus a squared, we said was expectation of z squared minus 2a times expectation of z plus a squared. Okay, now this is true for any number. Okay, for any number, we know what the expectation of z minus a squared is. Okay, now let us say we choose a number a. Okay, we choose a number such that it minimizes this expectation. Okay, so my question is find a so that okay, find a value of a for me. Okay, so that expectation of z minus a squared is minimized. Okay, how do we do this? No. How do we do this? Like, so this quantity is some function of a, right? So I'm thinking of this quantity is some function of a. Okay, so I'm not worrying about the random variable or anything right now. I'm looking at this as purely a function of a because I'm only going to choose a now. Okay, so what it literally means is find a so that f of a is minimized. How do you do this? And not f of a equals 0. You may not be able to make it equal to 0. Okay, but how do you find the minimum of a function? Right, you take the first derivative. Okay, so take the derivative of f with respect to a, and this must be equal to 0 at any extremum point of f, either the minima or the maxima. Okay, so this part is wherever you find a minima or a maxima. Okay, so this is like a this is necessary. Okay, right, so let's do this. What's the derivative of f of a? Differentiate this as a function of a for me.
Can I just speak it instead of type it?
Yeah, that's
2 expectation z to the first.
right. So minus 2 times expectation of z, okay, plus.
Oh, I totally did it wrong. So
Uh,
we're differentiating with respect to a, right? So
Right.
the first term goes to 0. We
Right.
keep on to the second term, and that's negative 2 expectation of z, and then plus 2 to it.
Right. Okay. Okay. If you can hear the car alarm go, like, I don't know what is happening. Okay. It's finally stopped. Okay. So this is minus 2 times expectation of z plus 2 times a equals 0. Okay. And this is or a equals the expectation of z. Okay, now this is necessary. What would be sufficient is the second derivative of f of a with respect to a should be positive. Okay, what's the second derivative of expectation of z squared minus 2az plus a squared?
It would just be 2, right?
Right, so this is 2, which is positive. Okay, so sure enough, this is minimized when a is expectation of z. Okay, so basically this is what we want. So z is a function. Okay, z can take on many different values. Z is a random variable, and depending on the outcome of your experiment, z can be many different values. Okay, because depending on the outcome of your experiment, z takes on a different value. Okay, but now I'm asking you, okay, I'm not interested in seeing all these many different values. Okay, give me one number a, okay, that has the minimum mean squared error. Okay, because if you give me one number a, it will not always match the value of the random variable. Okay, because I just have one number to pick from. If you choose a random variable based on the outcome of your experiment, you have potentially many different numbers that the random variable could throw up. Okay, but instead what I'll say is I'll just keep one value of a, okay, that hopefully captures your random variable. In what sense? In this sense, right? I look at the mean squared error. Okay, because I have just one number and you have a range of numbers, I'm going to make an error in many cases. Okay, I'm going to look at the mean squared error. Okay, so I'm going to take the square of what your actual value of the random, the square of the difference between your actual value of the random variable and the single number that I have. Okay, and I want the square of this error to be minimized on an average. Okay, then the best number I can choose is the expectation of the random variable. Okay, so here, so that is what we mean. So the expectation of z is the best mean square estimate for z. Okay, so it's the best estimate of c. Let's use the same, we are going to use this sentence later. Let me use it in the same form. So we could choose to look at different estimates. Okay, and that would be we could choose to look at an estimate that is not a single number. Okay, I can choose to look at an estimate that is some function of another random variable. Okay, so those are all different. Okay, they have much more power. Okay, but here I'm just looking at an estimate that is a single number. Okay, the nature of the estimator here is like it has to be just one number. Okay, I cannot change it based on the outcome of the experiment. Okay, it just has to be one number all through, right? So if that is the kind of estimate you're looking for, the best estimate in the mean squared sense of the random variable is the expectation. Okay, right? So we are good on this. Okay, so now let's look at, so I know we are almost out of time, but let's look at one last thing. So suppose x1, x2 to xn are independent Bernoulli random variables. Okay, so we have y to be x1 plus x2 all the way through xn. Okay, but because they are independent, y is now binomial. Okay, y is binomial means that the probability y equals k we can write as n choose k, p to the k, 1 minus p to the n minus k. Okay, so we know the full distribution. But let's say we want the variance of y. Okay, so I want you to try your hand at computing this. Okay, we know the expectation of y by linearity. right? So this is n times p. This we could do because of linearity, okay? But now the variance of y is the expectation of y's minus np whole square. Okay, now this is a quadratic function. Okay, it's not linear. Okay, so but I want you to try your hand at simplifying this. Okay, so we'll take this up next class. Okay, but try your hand at simplifying this as best as you can. Okay. Okay. So we'll stop. We'll stop here, and we'll continue next class. But any questions? So we didn't yet come up to the question in quiz 8. Okay, but we'll do that next class. Okay. So you had told me like how to compute the probability of the events AI in the quiz. Okay. We went a little bit slower than I had anticipated, but we'll get to it next class. Okay. Okay.
Sounds good. Thank you.
Okay. Thank you.